Alright, we're doing friction, and we're in unit number 4. We're gonna wrap up. I'm gonna do page 18, and then I'm gonna do page 19. So I'll work through both of those pages. It's probably gonna take me, I don't know, take me a little while, but we'll get through it. All of this material I'm not going to cover in class, so make sure you watch all the way through the end of the video, especially example number 16 is going to be a big helpful example as you plow through the problem set over the weekend. So here it is. So you know that we have three kinds of friction. We have static friction, rolling friction, and fluid friction. And yesterday, on Friday, we spent some time going through static friction or kinetic friction, and we drug the blocks. We measured the coefficient of kinetic friction between the block and the tabletop, and we got a number, and we found out if we double the mass, the coefficient of friction won't change. All right, so we did coefficient of kinetic friction. We did kinetic friction. Now today we're going to focus on rolling friction or static friction. So you should know that static friction and rolling friction are basically the same names. They're synonymous. And so static friction occurs between two surfaces when there is no motion between the two surfaces. So as long as the two surfaces are not scraping against one another, we would classify that as static friction or rolling friction. All right, now we're going to go ahead and do a quick demonstration. I'm going to do it right on the video, and it'll probably take me a second just to get things kind of lined up and making sure that things are going to be working well. But I've got a block right here, and I'm going to hook to that block a scale. And let's see if I can kind of set this up so you can actually kind of read the scale a little bit. So what I'm going to do is I'm going to pull on the block. The block is at rest. Everything's at rest. And I want you to watch the scale reading increase and then see what happens to the scale reading when the block goes in motion. So it's that transition between at rest and in motion that I want you to observe. So you'll notice that the scale reading continues to go up, 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 and all of a sudden it goes. And notice it kind of went up to, I don't know if I kind of marked this on here, looked to me up in this region is where it got to. We'll do it one more time just to see how good we got. So little increase, and this time I'm going to continue to drag it a little further this time. All right, and then constant speed. And constant speed looks like it was right up in here. So I'll kind of mark that for constant speed. And then it looked like it got a little further on this one. I'll put an R for at rest. So I'll do it one more time. So increase, 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 and then there's constant speed right there. All right, now obviously it does fluctuate a little bit on the starting one, but it's someplace in this region up here. In motion is way down here. Notice it's not even close. This is really different compared to this number. All right, so what I want you to understand, I guess, is that when it climbs up to this region up in here, this would be roughly, let's see, 2 point maybe 7, 8 newtons of pulling force, of tension force. When it gets all the way up in here, the block's at rest. And if the block's at rest, that means we're dealing with static friction. Notice that once I got it going, the reading went down to here, maybe a little over 1, so we're talking maybe 1.1. So the force needed to get it going, that's static friction, is much greater than the force to keep it going. What does that tell us about the difference between static friction and kinetic friction? Well, the difference between them is this. Static friction is much greater than kinetic friction. And you would think that would be weird, but it takes a lot more force to get an object going than to keep an object going. Once it's going, you really have inertia working for you. An object in motion tends to stay in motion. To get it going, you got you got inertia working against you. An object at rest tends to stay at rest. It's staying at rest. So static friction is greater than kinetic friction. So let's see if we can kind of put those numbers down on paper. So here's the sheet. Here it is, demonstration, velocity of the spring. Static friction, what did we say? I'll kind of bring this back in. I think we were saying right in here, right around 1.7. All right, and then kinetic friction was, I think, 1.1 newtons. Notice the difference. So the big thing I want you to carry away from this is that static friction is much greater than kinetic friction. We're going to come back to that in just a moment. Okay, factors that affect static friction. The factors that affect static friction are the same factors that affected kinetic friction. One was the coefficient of friction, which is a number that describes the texture or the roughness of those two surfaces. And the other one is going to be your normal force. So those two are the same. So we have an equation for static friction and kinetic friction, and this is the same one. It works for both of them. So we have an equation for fluid friction, all right, and that was 1/2, I think, what was it, v squared, I think rho was in there, a, and the drag coefficient, all right, and then we have one for static friction and kinetic friction. So this is one and the same for both of those. All right, just like we had a number for the coefficient of kinetic friction, we also have a number for coefficient of static friction. Notice that we put an S right in there. So this is a number that describes the texture, so it's the same idea, or amount of friction between two surfaces when the surfaces are at rest relative to each other. So the big difference is static friction is the texture while they're at rest, and kinetic friction is the texture while they're in motion. And we'll find out that the coefficient of static friction is going to be greater than the coefficient of kinetic friction. And that's what we're going to say right here. So static friction is going to be less than, I said that wrong. Static friction is going to be greater than kinetic friction. And there are two reasons for that. The first reason is the fact that you have inertia I'm not sure if against is maybe the best word, but it's inertia. Inertia is working against static friction. An object at rest wants to stay at rest, and you're trying to overcome that. So it's going to take a lot of force to get it going. Inertia is actually working for kinetic friction because it's already in motion. All you have to do is just keep it going. All right, number 2 is the grooves. And I think there's one O in there. So once the object is at rest, the grooves interlock, and it's going to take a lot of force to get them going. But if the object is already going, those grooves don't have a chance to get completely locked, and it doesn't take much force to keep it going. Once it's at rest and those grooves get interlocked, hard to get it going. You have to overcome that, and that's another reason that coefficient of static friction is greater than the coefficient of kinetic friction. All right, and then if you just look at the table down below here, this is table 4-1, I have the coefficient of friction static here and kinetic here for a number of different types of surfaces. This is aluminum on aluminum, glass on glass, rubber on concrete when it's dry and then when they're wet, steel on aluminum, steel on steel when it's dry, and then when it's lubricated, and you get the idea. But look at, the big thing I want you to look at is, regardless of which one you're looking at, the coefficient of static friction is greater than the coefficient of kinetic friction. And that's true all the way down. Now what I find is interesting, one of the lowest types of frictions that are out there is the synovial joints, which are the joints at the end of most long bones like elbows and hips. there is very, very little friction between them. And that's a good thing, because if if there was a lot of friction between your joints, your joints would warm up, and then that would probably be a good thing. It'd heat up, and we don't want that. So they stay very nice and lubricated. All right, let's look at example 14. It says if you must suddenly slow your car down from rest to high speeds, you're not advised to lock the wheels of your car. And here's the how come. When I was taking driver's ed, this is back in 1986, a long time ago, they advised us that if we wanted to come to rest, we had to pump the brakes. So instead of laying on the brakes really hard, they wanted you to pump the brakes. And the idea is this: if you lock your brakes, your wheels stop turning and you'll skid to a rest. That's kinetic friction. But if you pump your brakes and you prevent your wheels from locking, then you'll roll to a rest. And that deals with rolling friction or static friction. And we just saw right here that static friction is greater than kinetic friction. So there's a lot more friction there that you can draw on to come to rest by rolling to rest as opposed to sliding to rest. Nowadays, cars have anti-lock brakes, and I've heard, I don't know how true it is, I've heard that the car will actually pump your brakes for you. So in some cases, you probably want to just go ahead and lay on your brakes, because the car will take over and prevent your tires from locking, and you'll actually then roll to a rest as opposed to skid to a rest. So that's example number 14. Flipping over, we're going to example number 19, or example number 15. All right, example number 15 is a question that is a wonderful question, because we're going to do it in this chapter, and then I think we're going to do it in the next chapter as well. So let me read it to you and see what we can get out of this. So it says, a hockey puck slides off the ice and onto another surface with a coefficient of kinetic friction of 0.4. Now this is kinetic, so it's in motion. If the hockey puck is sliding at 20 meters per second, how far will the hockey puck travel before it comes to rest? So that's a lot of information. The way that we want to attack this problem is free body diagrams. Let me make a comment about them. I know that you probably may not be real used to free body diagrams, but I highly recommend that let the free body diagram be your starting point for a majority of the problems on the problem set. And you know that if you start with a free body diagram, you're going to go to Newton's second law, and that's what we're going to do on this one. So we have a hockey puck, and here it is here, and it's in motion, and we're going to say that it encounters a new surface. So it slides off the ice, so this is ice, and onto some new surface, and then it's going to come to rest. And so let's basically draw the forces. So the question is what forces are acting on the puck as it comes to rest? Well, you know that we have weight, and the surface is pushing up, so that'll be the normal force. And then nobody's pushing on the puck. Well, I'll get to that in a moment. Let me do the other part first. Since the puck is moving to the right, we're going to have friction acting to the left. Now let me address the other one. A lot of people want to put an arrow this way and maybe call it speed because it's moving at 20 meters per second. Look at 20 meters per second. 20 meters per second is a speed, and we're looking for forces like normal force, friction, weight. Those are all measured in newtons. Remember, an object in motion tends to stay in motion, so we don't have to push the puck forward to keep it going. Once it's going, its natural tendency is to keep going. All friction does is slow it down and bring it to rest. So its inertia keeps it going. It's friction that brings it to rest. And inertia is not a vector, and so we don't want to put an arrow on there. So the only forces we have acting on this are going to be those three. So let's kind of look at what we want. It says the question asks for how far will the hockey puck travel. Well, we know if we start Newton's second law, here's the x direction, and then here's the y direction. We don't have what we want. I mean, we want how far, and how far is not going to show up here. So we kind of need to go to the big three, and I'm going to go ahead and start the big three down here and let this be a kind of a guide to my thinking. We know how fast the puck is moving at the beginning. We know it's moving at 20 meters per second. And we know it's going to come to rest. So our final velocity is going to be 0. The problem is I need this, and I don't know the acceleration of the puck, and I don't know how long it's in motion. I know neither of those. So I need to use Newton's second law to get my acceleration. So this is kind of a two-step problem, and you're going to find that on the problem set that's going to be the case for a number of problems. You'll either do the big three. You'll use Newton's second law to get the acceleration in big three, or you use the big three to get the acceleration in Newton's second law. It's one or the other. So we're going to go ahead and use Newton's second law, and I know that in the x direction I only have one force. That's the force of friction, and it's to the left. So I got force of friction is equal to max. Now, here's the scoop on this. I am accelerating. I am slowing down, so I can't say that this is 0. I can't cross it out. But I need the acceleration for the big three, and I don't know the coefficient. I don't know the force of friction. Now, let me say this. At this point, a lot of people think, let me scoot the paper over just a little bit, that the kinetic friction, the coefficient of kinetic friction, goes in for f of f. Remember, f of f is a force. It's measured in newtons. This coefficient of friction has no units. I can't plug 0.4 in for force of friction. It doesn't work that way. Alright, so then I have to kind of recall a couple equations, and this is an equation that you're going to have to start recalling pretty darn quick. You need to remember that force of friction is mu Fn. So I'm going to make that substitution. So I get mu Fn is equal to max. I'm going to solve for ax because that's what I want. So ax is equal to negative mu Fn over m. And then let's think this through. Well, I know what the coefficient of kinetic friction is. That's 0.4. So I've got that one. I don't know what the normal force, and I don't know what the mass is. So I'm kind of stuck. There are things I don't have. And when you get to this point in your problem set or on the test and you get kind of stuck, remember you've got this guy sitting over here. Let's use him because he might give us some things we want. So in the y direction, we have the normal force and we have the weight. So I'm going to go ahead and plug those in. So the normal force minus weight is equal to, now in this case, the puck is only moving sideways. It's not moving up and down. So the acceleration vertically is 0. So that means that's all gone. So I can say that the normal force is equal to the W. And now look at that. I want the normal force, and I have now an expression for the normal force. That's equal to the weight. So I'm going to substitute that over here. And this is a big step that you're going to have to be able to do when you're working through these problems. All right, one couple more last steps here. Okay, so I know coefficient of friction. The problem is I don't know what weight is, and I still don't know what mass is. But I remember that weight is equal to mg. So I'm going to make that substitution. So I got negative mu mg over m. Cancel those out. So then my acceleration is equal to negative mu g. So I can actually plug that in right here, negative mu g. So I need an equation, I need a big 3 for the distance that doesn't have time. And I'm trying to think. Actually, I think I could use this one. Let's try this one real quick. So I've got Vf squared equals Vo squared plus 2AD. If you remember, my final velocity was 0. If I want D, I'm going to move Vo to the other side. That makes it negative. And then divide by 2A. So D is equal to negative Vo squared over 2A. I have an expression for A. Remember that one? It was the negative mu g. So I'm going to slip that over. So D is equal to negative Vo squared all over 2 times negative mu g. Plus, my negatives cancel. So I get Vo squared over 2 mu g. Alright, we have everything now. I know the speed, I know mu, and I know g. So I'm going to plug them in. Vo is 20 meters per second. 2 8.4. I'm going to use 10 this time. And if I plug them in, if I plug all that in, I'll get 50 meters. The puck will travel 50 meters on this new surface. Alright, so we have a couple questions at the end. And here it is. If the mass of the puck was doubled, the distance the puck travels. Alright, let's look at this. Let this piece right here guide your thinking. Notice, we don't have any masses. The masses actually canceled out over here. Since mass doesn't show up over here, it'll travel the same distance. It has no effect. Now look what happens if I take the initial speed and I double the initial speed. I'm going to do this in a different color so you can see how this works. If I double the initial speed, I'm going to use some over here. Look at what happens. I'm going to use this equation. I'm just going to rewrite it over here. I'm going to double that initial speed. So I'm going to get 2 times that speed over 2 mu g. Now this 2, this square, operates on the VO and it operates on the 2. So watch what happens. That becomes 4. There's VO squared over 2 mu g. Now notice, look at what happens. This is what I used to have, which is right here. But now it's 4 times what I used to have. So whatever my distance used to be, 50 meters, it's going to be quadrupled that. So 4 times 50 is going to give us 200 meters, or 4 times what I originally had. Just a note real quick before we move on. We're going to solve this same problem in unit number 5 when we use work and energy. So we use the big 3 and we use Newton's second law to solve it here. Next chapter we'll use something different and we'll get the same answer. So just a mental note on that. Alright, the last question that we're going to run through is example number 16. And example number 16 says, a block of mass 13.2 kilograms lying on an inclined plane is connected to a rock of mass 1.2 kilograms by a very light cord. I'll tell you what that means in just a moment. Passing over a pulley as shown in the diagram below. Obviously you don't have a diagram, so I'll help you with that. Determine the acceleration of the block given a coefficient of friction of 0.15 and an angle of elevation for the ramp of 25 degrees. Consider the mass and friction of the pulley to be negligible. Alright, so let's do a diagram and we'll help you get that started. So we're going to have a big triangle, an inclined plane. We're going to have, sounds like we have a block on there, and that block is attached to a rope and a pulley and some sort of rock that's hanging there. Alright, so the first step is to, just like we did the previous problem, draw a free body diagram. So we've got the weight coming down. We know that the weight has 2 components. We have the weight in the x direction. We have the weight also in the y direction. This is theta. This is theta. We also have the normal force. And since a string is attached to this block and that string is pulling on the block, we also have tension. Alright, now, we need to kind of get used to renaming a lot of these forces. Look at this Wx. Wx is opposite my theta. Here's my hypotenuse. Here's my theta. So opposite means sine. So it's going to be W sine theta, and that's also equal to mg sine theta. That'll come in handy in a bit. We can do the same thing down here. It's cosine in this case. And then mg cosine theta. Let's do one more with the tension. Why is there tension? There's tension because of this rock right here. He's hanging down. He has some weight. I'm going to call him WR, the weight of the rock. The weight of that rock is spread evenly through this tension in this cord. So if the rock was 5 newtons, the tension in the cord would be 5 newtons. So the tension in the cord and the weight of the rock are the same thing. So instead of saying tension, I'm going to call it weight of the rock. Okay, So we want acceleration. I'm going to scooch this over a little bit. And once I draw a free body diagram, the next step is to do Newton's second law. And I'm going to go ahead and do it in the x direction and in the y direction. So Newton's second law in the x direction. And we'll do Newton's second law in the y direction here in just a moment. All right, so what forces are acting in the x direction? Well, I've got two of them. I've got the tension and I got Wx. And I'm going to go ahead and put them down. So I got negative tension plus Wx. And, I forgot one. They mention friction, so friction is going to play a role in this. So friction is going to oppose motion, so we also have friction. So I've got force of friction acting to the left. So I've got three of them in the x direction. Sorry about that, missed that. All right, so that equals max. And they say that the object is in motion. So we know that this is not going to be zero. It's accelerating. It's picking up speed along the way. So I'm going to solve for ax because that's what I want. So ax is equal to all of this stuff. I'm going to kind of move things around a little bit. So it's still wx minus t minus f of f. And then I'm going to spend some time renaming these guys. And I have their names right over here. So ax is equal to wx is going to be mg sine theta. The tension is the weight of the rock, so that's going to be Wr, and minus friction, which is mu Fn. Remember, I got to remember that force of friction is the same thing as mu Fn. All right, all over m. All right, I'm going to take a quick peek and see what I actually know. They do tell me the mass of the block, so I do know that. That's 13.2 kilograms. I know g, I know the angle. Do I know the weight of the rock? Well, I know the mass of the rock, but I don't know the weight of the rock, so I don't know that one. I know mu. Mu is going to be 0.15, but I don't know the normal force, and I do know this. So I got two things I don't know, so I have to rename them. Well, I know that weight is equal to mg, so I'm going to go ahead and rename that. So I've got mg sine theta minus mass of the rock times g minus mu Fn all over m. Alright, I'm going to zoom in just a little bit so you can kind of see what I have. So I know the mass of the box, I know g, I know theta, I know the mass of the rock now, that's 1.2, I know g, I know mu, I don't know the force of, or the normal force, but I do know the mass of the box. So there's one thing. And you're going to find out that if you don't know the normal force, the way to find normal force is to go in the y direction and grab it. So we're going to scooch this over. And we're going to sum up all the forces in the y direction this time and plug everything in. So in the y direction, what forces do I have? Well, I've got two of them. I've got the normal force and I've got Wy. So I'm going to plug both of those in. So I've got the normal force is positive minus Wy. Now as this thing accelerates down the inclined plane, it's not going to accelerate in the y direction. It's going to stay connected to the plane. So the acceleration in the vertical direction is 0. It doesn't accelerate in the y direction. I'm not sure if I said that right. The acceleration in the y direction is 0. It stays on the plane. All right, so I need an n. So n is going to be equal to Wy. But I know that Wy, this is where these nicknames come in handy. Wy is actually down here. It's mg cosine theta. So n is equal to mg cosine theta. And then I can make one last substitution. I'm going to go right there, okay, because that's what I need. So one last substitution, then we'll plug numbers in, which is what you guys all want to do. So the acceleration is equal to mg sine theta minus mass of the rock times gravity minus mu times, I don't need to use parentheses, mg cosine theta all over m. There it is. We got it. We know everything. So the last step is plug everything in. So I go ahead and do that. So AX is equal to mass of the block is going to be 13.2 kilograms times the acceleration, which is 9.8 meters per second squared, sine of 25 degrees minus the mass of the rock, 1.2 kilograms, times g, 9.8 meters per second squared, minus mu, which is 0.15, times the mass of, which one is this? This is the mass of the box. So it's 13.2 kilograms. I'm running out of room. Times 9.8 meters per second squared. I'll stick the cosine up here. Cosine of 25 degrees all over the mass of the box, which is going to be 13.2 kilograms. All right, I'm going to plug this stuff in, and I'll kind of do it piecemeal. You can kind of watch me do it as I do it. So I'll kind of pull this up and plug them in with you. So let's see what we can actually get on this guy. So we're going to go 13.2 times 9.8 times sine of 25. Make sure I did that right. 13.2, 9.8 sine 25. That gives me 54 point, we'll say 7. I'll write that down over here. I know you can't see that, but I'll show you here in just a moment. Okay, the next one is 1.2 and 9.8. That's 11 points, we'll say 8, and that's going to be minus. The next one's a long one, so it's 0.15. Let me clear this off for you. 0.15 times 13.2 times 9.8 cosine of 25. And that gives us 17.6. That's minus, so negative 17.6. That's all divided by our mass, which is 13.2. So I wrote these down on the side over here. I'll show you what I've got. So there they are. And we'll plug them in and see what we get. So I'm going to do 54.7 minus 11.8 minus 17.6 divided by 13.2. And I get 1.9 meters per second squared. And there it is. Congratulations, you made it to end of chapter 4. On Monday, we'll do Q&A. Tuesday, Excel lab. And Wednesday, test. Good luck.